What's up, guys, and welcome to this video on question 4 of the 2015 supplementary exam. It's going to cover Newton's laws. Okay, cool stuff. Let's get straight into it. Okay, so we have two identical blocks A and B that is joined by a string and is being pulled by a constant force F across A. Frictionless, quite important. Let's mark that. Horizontal surface as shown in the diagram. So after a certain time t, the string between them breaks and the force continues to act on force B. So we need to draw the velocity time graph indicating the following points: A and B before t, A after t, and B after t. Okay, so let us get into that then. Let's draw a set of axes. Oh, that's pretty straight. Cool stuff. So we have velocity in meters per second, and we have time in seconds. Okay, so let's think about this. Okay, when the blocks A and B are coupled up before the time t, they're moving at the same they're moving together and they're moving as one system, so they have the same acceleration. Okay, so let's put in a 0 right there. It's going to look something, let's say, like this. We don't know what the gradient is because we don't know the times, but we do know that this occurs at time t. Okay, so cool stuff. So that is A and B. So that's our first point. Okay, let's just put 0, 0, 0, 0. Okay, so that's our first part of the graph done. So now we need to know A after the time t. Okay, so let's draw a Freebody diagram, okay, of A. So we have the mass times the gravity and we have the force, normal. But we have no horizontal forces. We have no forces acting on it because the string is now broken and there's no frictional forces. So if there's no forces acting on this body, it's going to continue at a constant velocity. So that's going to be A. Okay, so we've got A after time t. Now we need B after time t. So let's draw a Freebody diagram again. Okay, so we have, this is B, and we have mg, we have force normal, and we have F. Okay, so before that we also had this right here. So the mass before the string gets cut is greater than the mass after. Okay, but we cut the string right there, so that part falls away. So what we're left with, if we write Newton's second law, we're left with F equals ma. Okay, but the force is constant, so the force remains constant before and after the string is cut, but the mass has now gone down after the string is being cut, so our acceleration must go up in order to balance this. So what we end up with having is a much steeper acceleration. Let's say something like that, and that's for B. And there we go, 3 marks right there. So now we look at the second part. Okay, identical strings, identical situation. This time, however, we have a rough horizontal surface and it is traveling beforehand at a constant speed. Okay, again the string gets cut and we have the same situation. So again we have V in meters per second, we've got T in seconds, and we have our origin 0, 0. But this time A and B were moving at a constant velocity. So until time t we have that situation, and we have the point t. Okay, let's draw our Freebody diagram for A. So I'm not going to draw the mass and the normal force, I'm just going to take into consideration the force of friction. So in this situation, friction is acting, and friction is always going to slow down the object, and it's going to slow it down all the way until it comes to rest. So that's A and B. That's A. Just want to make sure I labeled that. Yep. Okay. So now let's look at B. B, again, we're going to have a very simple situation. We have F, but this time we have a force, friction acting on it. So what we can say is it's going to increase like this graph right here again, but it's going, because friction is acting, the gradient is going to be actually slightly a less gradient. We're going to have a lower gradient, so it's going to look maybe something like that, and we have that as being B. And we've got all 3 sections and we've got our 3 marks. Cool stuff, happy days. Okay, so let's go on to the next question. Okay, 4.3. 2 different blocks, A and B, of mass 16 and 24 kilograms, are placed across a smooth frictionless surface, again by that same rope, and we have an angle 64 degrees shown here, right there, quite nice. The rope Y exerts a force of 120, which is again shown in the diagram, and the blocks joined again by nothing. The mass of the ropes X and Y are negligible compared to that of the block. Okay, cool stuff. So they've actually given us a very nice diagram showing you exactly what's happening. Okay, Newton's second law. Okay, that's three marks because it's a definition. I'm not going to write the definition, but essentially it says that we can say that when a net force is applied on an object, it accelerates in the direction of the net force, and the acceleration is directly proportional to the net force and inversely proportional to the mass. So all this is telling us essentially is that F net is equal to ma. That's the most important part of Newton's second law. Okay, so we want to calculate the magnitude of the acceleration of both blocks A and B. Okay, so how are we going to do this? Okay, so we're going to start off by doing a free body diagram. So let's say 4.3.2. Okay, so we're going to start off by a free body diagram, and I'm going to do it for the system. So we can isolate a free body diagram. So we could do a free body diagram for A, we could do one for B, or we can do one for A and B, which is what I'm going to do, which basically takes into consideration this entire system. So it's going to look something like this. So a free body diagram looks something like this. There's no friction. We've got a force normal. We've got mg acting, and we've got our force friction, or our force applied, with 120, and this angle right here is 64 degrees. Okay, so what can we do with this information? Okay, so now let's do the sum of the forces. So we're going to do the sum of the forces in that direction, or right, equal to mass times acceleration in that direction right there, because we're looking for the acceleration of the blocks A and B. Okay, so let's think about the forces acting. So we have this force, this component of the applied force, which is equal to F net, or let's not make that F net, but let's say that this is force applied, and that's going to be cos of 64 is equal to, there's no other forces acting, so it's equal to mass, but the mass is going to be the total mass, so that's going to be 16 plus 24 times acceleration. Okay, and putting FA in, we're going to have 120 cos 64 is equal to 40A, and so putting this into our calculator and solving for A, we get acceleration is equal to 1,32, and what are the units for acceleration? Meters per second squared. Okay, and again, once the magnitude, so we don't care about the direction. But if we did care about the direction, we would say that it is acting right. Cool stuff. So we get nice 4 marks. Okay, then it says draw a free body diagram to represent the forces acting on block A only. The labels must have the names of the forces, not just symbols. Okay, so we want to draw a free body diagram. Okay, so this is 4.3.3. Okay, so we start off with, okay, so we're drawing a free body diagram. So we've got a circle there, and the forces acting on A, okay, so we've got weight. Okay, then we've got normal force, and we've got the force of tension. Okay, another way of doing this that you can do also is you can say that this is Fn, this is we can say Fg, and this is Ft, and then on the side you have a key that says Fn equals normal force, and Fg equals weight, and Ft equals tension, or you can do it the way I've done it and just given them values right there. So either case doesn't really matter. Okay, let me give myself a little bit of space. I'm probably going to need a bit more than that, so I'm going to just take it down. Okay, I'm sure we'll be fine for that. Yeah, and that's 4 marks for drawing that. And let's just put in that this is A. So this is the system right here. Cool stuff. So let's go on to the next question. 4.3.4. Okay, calculate the magnitude of the tension in X between blocks A and B. So this is the rope that we really care about. Okay, so we're going to use, so we want to calculate the magnitude of the tension. Okay, so we've already drawn the free body diagram. Oh, wait a second, calculate the magnitude of tension of, yeah, so we've already drawn the free body diagram for A, so I'm just going to use A. So what we're going to say is the sum of the forces in that direction as being positive is equal to the mass times the acceleration in that direction, which is positive. Okay, and what are the forces acting in that direction? We have tension is equal to the mass of A. Remember, we're looking at A now, which is 16 kilograms, times the acceleration of the system, which we calculated as 1,32 meters per second. And so the tension between A and B is equal to 21,12 units of newtons. And again, they've been nice to you and they've said magnitude, but if they didn't and they said they wanted a direction, it would be for block A, it would be right. Again. Okay, cool stuff. And then it says calculate the work done by rope Y on the system if the work done by rope Y on the system as it pulls a block a distance of 5 meters. Okay, so what if we look at our system, so we want to know the work done by this rope right here. Okay, so what we're going to do is I'm going to use 4.3.5, so 4.3.5. Again, I'm going to look at the full system, drawing a quick free body diagram, 120, okay, and this had a mass of 40. Okay, so work, we can say, is equal to the force times the distance. Yeah, so Fs, let's say. Okay, and the force, the actual work that's actually being done is the force in that direction. So again, we have, it's going to be equal to 120, and this angle was 64. 120 cos 64. So that there is our force, and our distance we know is 5 meters. And so our answer comes out as being the work is equal to 263,02. And what are the units? Units of joules. And we don't have a direction because it is a scalar. Okay, cool stuff. And again, we get a nice 4 marks. Okay, so as you can see, it's not too difficult, nothing too hectic, but yeah. Okay, so we can go into the next question. A block of 15 kilograms is at rest on a rough horizontal surface. The block is placed by means of is pulled rather by a rope, which exerts at 55 degrees. As you can see, the maximum force which the rope can exert before the block starts to move is 80 newtons. As we can see, calculate the coefficient of static friction. Okay, cool stuff. So what are we going to start out by doing? Okay, so always with one of these questions, let's do it right here. Let's see if I can take that off. Okay, let's make that bigger. Move that, and let's get back to my black. Okay, so we're going to do question 4.4. Okay, always start with a free body diagram of the system. Okay, so we have our 80 newtons, we've got 55 degrees, we've got force normal, we have mg, we've got force friction. Okay, cool stuff. And then I'm just going to put in these right here. This is F parallel, and this is F okay, now let's rather name these. So let's say that this value is f, so this is f cos 55, and this is f sine 55. Okay, cool stuff. So I want to calculate the friction. Okay, so how am I going to go about doing this? I'm going to say that the sum of the forces in that direction is equal to the mass times the acceleration in that direction right there. Okay, this right here gives us a very important piece of information. When the maximum force is applied, it's going to be traveling at a constant velocity. When it's traveling at a constant velocity, we can say that this term goes to 0. Okay, so now we're just dealing with the sum of the forces in the right direction. Okay, so start that again. Okay, so what about forces? Okay, so we can say that this is a positive force. This is a positive force right here, so we can say that F cos 55 is positive. Okay, minus force friction is equal to 0. Okay, so the force friction is equal to F cos 55. Okay, now the question is, what is the force friction? So the force of friction is equal to your normal force times mu, or your F normal times mu. So now the question is, what is your normal force? Okay, so your normal force, so let's see, F normal. Okay, so to figure out your your normal force, we have to do this. So we have to take the sum of the forces. Let's say what direction we want to give it. Let's say sum of the forces down is equal to mg down, but this again is equal to 0. Okay, so our normal force. So our forces down would be mg, okay, minus f sine 55 is equal or plus minus force normal is equal to 0. So our force normal is equal to mass. So the mass is 15 times 9.81 minus 80 sine 55. Okay, and what we end up with is our normal force equaling 81,468 units of newtons. See, okay, units of newtons. So that's our force normal. So our force friction is equal to 81,468 mu. Okay, and we can say now we have force friction in terms of mu. We know what F is, and we know what cos 55 is. So we can say that 81,468 mu, that's the force friction, is equal to F, which is 80 cos 55. And then we just solve for mu. And we can say that mu is equal to 45,866 over 81,468. And so mu is equal to 0.56. And what are the units? No units. Good stuff. So that's our final answer. And mu is less than 1, as we would expect. And so we end up getting 6 marks for that. Yeah. So I hope that was useful for you guys. Yeah, I had to do a bit of the work on the side here, but hopefully you guys were able to follow that quite easily, and it wasn't too difficult. Okay, so that's question 4, done and dusted. 6 marks right there. So in the next video, I will be covering question 6, I think. Yeah, so thanks for watching, guys. I hope you found it useful. If not, then leave me a comment or send me an email and I will redo or try and clarify something. Okay, thanks for watching, guys.